So a topic that usually comes up in the context of infinite series is to ask whether the series converges or diverges. And we've seen two instances where we can determine that a series converges by actually finding its value, finding what it converges to. And that was the case of the telescoping series, where we used the definition of the sum of an infinite series directly to find the sum. And then, of course, in geometric series, we have this nice formula where you can tell just from looking at the common ratio whether a series converges or diverges, and if it does converge, you can actually find its value. In most cases, though, we're going to be able to ask the question whether a series converges or diverges without actually finding what it converges to, if it does converge, without really calculating anything. This is sort of analogous to what we did in the case of the of improper integrals, where where we had the comparison test that could tell us that that a particular improper integral converged even without finding its value. So we're going to be learning a series of tests throughout the next couple of sections. The first of these tests is the easiest one to use, and it's often called the Nth Term Test or the Divergence Test. I think our book calls it the Nth Term Test for Divergence. So that test can be stated very, very simply, which is, right here, if the limit as n approaches infinity of an does not equal 0, then the sum of an, in other words, the series formed by the sequence an, diverges. So what this means is an is some sort of sequence, and we look at whether the limit of the sequence is not 0. If it's not 0, then the series formed from that sequence diverges. Now, I've put up here an equivalent statement. You notice that if we're saying that if the limit is not 0, then the series diverges, then that's logically equivalent to saying that if the series doesn't diverge, in other words, if it converges, that means the limit has to be 0. Some of you would have learned you probably learned a little bit about logic at the beginning of geometry class, where you learned if hypothesis then conclusion is a conditional statement, and this is logically equivalent to if not conclusion, then not hypothesis, or you may have learned it as P implies Q is equivalent to not Q implies not P. If the symbolic logic confuses you, don't worry about it. The point is these two statements are logically equivalent to each other. The one in green and the one in purple are. So what's perhaps more important, though, is to recognize what the nth term test does not say, or what it does and doesn't say. It does say that if the limit of an is not 0, then the sum of an diverges, and it also says that if an converges, says equivalently, if an converges, then the limit of the underlying sequence is 0. The misinterpretation that people often attribute to this statement is if the limit of the sequence is 0, then that means that an converges. It's sort of natural to say, well, if the limit is not 0, then an diverges. That must mean that if the limit of an is 0, then sum of an converges. But that is not true, and that's why I've labeled that here to be a very, very bad misconception. It's not the case that the converse of a theorem is true necessarily. Sometimes it is, sometimes it isn't. But in this case, this is not a true statement. So what can you infer if you find the limit of the sequence and discover it's 0? The answer very simply can be explained by this one word: nothing, with 3 exclamation points after it. That's what you can infer if the limit is 0. So this is one of the hardest concepts that we're going to be covering, is being very, very careful about what it is a theorem says and what it doesn't say. So let me first of all just give you some intuitive sense of why the nth term test is true. So here I've sort of tried to depict here what a sequence looks like. I've got A1, A2, A3, and A4, and as you can see, they're all approaching. As we increase the index to higher and higher values, these numbers are approaching 0. So even though we're adding up, we can imagine that if each of these has a width of 1, it's like we're adding up these numbers. Eventually, as I get far enough along, it's sort of like I'm just adding 0. Now, on the other hand, if you look at the purple sequence on the right, here I'm adding. Once again, I'm just showing through area like what I'm adding together. I'm adding B1 plus B2 plus B3 plus B4 and B5. And as you can see, this sequence, I've written it so that it approaches the number 0.1, a very small number, but still, since these numbers aren't these terms of the sequence aren't getting any lower than zero point 0.1. When I add up all infinity of them, it's sort of like I'm adding zero point 0.1 times infinity, which of course just equals infinity. This is what happens if the sequence approaches any number that isn't zero. It's like you're just going to be adding up an infinite number of times a finite number. The only way the series has any hope of converging is if its sequence approaches zero. Now that doesn't guarantee that it converges. That just means that it could converge. If it doesn't approach zero, such as in this picture on the right, then it can't converge. That's what the nth term test is saying. So let's use the nth term test. Ask, does the sum from n equals 1 to infinity of e to the 1 over n converge or diverge? Well, what we can do is simply observe that the underlying sequence is defined by e to the 1 over n. Let's find the limit as n approaches infinity of an, which equals the limit as n approaches infinity of e to the 1 over n by the composite limit rule, that is e to the limit as n approaches infinity of 1 over n, which is limit as n approaches infinity of 1 over n is 0, and e to the 0 is 1. Well, we can conclude that 1 is not equal to 0. Therefore, by the nth term test, the sum of e to the 1 over n diverges. And we've proven that, so we write our little end of proof symbol, and with the flowers we are done. Okay, so that's an example of a proof using the nth term test. And by the way, I've put here the word nth term test, or you could call it divergence test, that we understand both of those. The point is that when you're doing one of these proofs, you want to say which theorem you're using, which test you're using, because we don't just sort of make arguments like this does or doesn't converge based on some kind of loose reasoning. Whenever you're stating that a series converges or diverges using a test, you are invoking that test. You should make it very clear which one you're using so that you can show that all the conditions required by that test are in fact satisfied. Now let's consider this one. I want to do this problem just to demonstrate the common mistake. So let's see. This is a series, and its underlying sequence is that term. So an is equal to 1 over n. Let's use the nth term test to calculate the limit as n approaches infinity of an, which is the limit as n approaches infinity of 1 over n, which is 0. So what happens when we perform the nth term test and the limit that we find is 0? The answer is we don't know whether the series converges or diverges. It's tempting to say, well, it wasn't not 0. Not 0 would mean that it diverges. Therefore, we got 0, so that must mean the series converges, but that's not the case. If limit of an is equal to 0, then nth term test is inconclusive and says nothing about convergence or divergence. Now, so we don't know the answer to this. How would we resolve it? Well, the answer is we'd have to use a different test, and we're going to learn some different tests in the coming sections. One thing I want to point out, though, is a lot of people will say, well, what do you mean it doesn't converge? Didn't we evaluate this limit? We evaluated the limit of an, and we got zeros. Doesn't that mean that it converges to 0? Well, that comes down to the question of what the word it refers to. When we say that it converges, what you're saying is that this sequence, an, converges to 0. That's true. But what we're doing with the nth term test is we're asking what value the sequence converges to as a way of determining whether the series converges. So recall, this was a very important distinction. There's sequence and there's series. We have to keep straight which one we're talking about. So it is true that the sequence an equals 1 over n does converge to 0, but its corresponding series, it turns out, does not, but there's no way to tell that through the nth term test. I know, that's kind of confusing, but that's the way it works. Okay.